knots and manifolds, which called Gehring-Martin-Tan number and Tan numbers. First of all, where does quantum and classical topology meet hyperbolic geometry and the group PSL2C? As we know, there exists now Thorsten-Perelman theorem about geometrization. Every closed free manifold can be decomposed in a canonical way into pieces that each have one of 8 types of geometries. And one of 8 Thorsten geometries is the geometry of the hyperbolic space H3. An array of free manifold is said to be hyperbolic if it is the factor of the hyperbolic space under the action of a discrete torsion-free group of orientation-preserving isometries. And by rigidity theorem, given a compact free manifold, which hyperbolic and which have finite volume, if this manifold has a geometric structure, hyperbolic structure, then this structure is unique. And it is known that the group of all orientation preserving isometry of hyperbolic free space is PSL2C. As I said, we will discuss numerical invariance for hyperbolic manifolds and hyperbolic manifolds. First of all, I'll recall some things about the group PSL2C. We know that for any matrix from SL to C, the trace and the norm are defined. We call matrix M such that not trivial, elliptic, parabolic, or hexagonal if the following conditions hold. And PSL2C is the factor group of SL2C by its center. And we call element from PSL2C elliptic, parabolic, hexadromic, if so its representative in SL2C. We will consider PSL2C as topological group, where we find topology, consider PSL2C with the working topology of matrix norm. And a subgroup G of PSL2C is said to be discrete if it is a discrete set from this topology. What does mean Jorgensen numbers, Jorgensen group? Recall that in today's talk, when I say H3, I mean the Poincare half-space model of H3 and identify the boundary of this space with the extended complex space C bar. The group PSL2C acts on H3 as the group of all orientation preserving isometries and on the boundary as the group of all linear fractional transformations. A subgroup G is called elementary if there exists a finite orbit in the closure of hyperbolic free space. Otherwise, it is non-elementary. All elementary discrete subgroups of PSL2C are classified, and they will be in the second part of my talk. And now we introduce this definition because we're interested in Jorgensen inequality theorem. Suppose that we have 2 elements, F and G, from PSL2C, and these elements generate a non-elementary discrete group. Then the following inequality on traces of these elements holds. This first of all, it was a technical lemma in Thorsten walk, but now it is a useful tool for, and this theorem have many corollaries, and we will consider left part of this inequality denoted by J of pair of generators, and let us consider 2 generated elementary discrete subgroup of PSL2C and the value infimum over all generated pairs of G capital over J is called Jorgensen number of G. We understand that this number is greater or equal 1 by Jorgensen result. And it is interesting that there exist groups such that they are to generate a discrete and elementary, and there exists a generating pair for which Jorgensen number is equal 1. We will refer to this group as extreme group for Jorgensen inequality.
Can you show the previous slide for a moment for definition of J and G?
This is on the left part of Jorgensen inequality. Some function on trace, square root, and trace of commutator of generators. Okay.
But the fact that it is not symmetric.
It is not symmetric.
So if you exchange, so there is a second inequality also.
Yes, yes, and that's why we consider only generating pairs of the group. The role of first generator in this modulus, but the trace of two elements is not trace of G and GF. Okay, it is interesting that there exist an infinite series of extreme groups for Jorgensen inequality. Obviously, PSL to R is a subgroup of PSL to C. And the only extreme subgroups of PSL to R are triangle groups with signature 2, 3, and n, where n greater or equal to 7 or n equals infinity. What does it mean? Let us consider the tessellation of hyperbolic plane. First picture is tessellation by triangle with angles pi over 2, pi over 3, pi over 7. And second is the tessellation by triangle pi over 2, pi over 3, pi over 8. And the last is the tessellation of modular group. For the case when triangle group have at the last place infinity. So what does this group mean? We consider the triangle with angles pi over 2, pi over 3, pi over n on hyperbolic plane, and consider the group generated by reflections on its edges. Then consider the subgroup index 2 of all orientation preserving isometries in this group. We denote this group by T with signature 2, 3, n. Another interesting result about relation between PSL to C and Jorgensen inequality, Jorgensen numbers, is following. Jason Callahan, in his PhD dissertation, calculate numbers for Knot groups. When I talking something about Knot group, I mean the image under faithful representation of this group in PSL to C. And it is interesting that only that figure 8 knot group is the only torsion-free extreme group. Other groups are not extreme. It is also known, it was proved by Sutter, that the Whitehead link group is not extreme. For this group, the number, Jorgensen number equals 2. And there exist other interesting results. Sutter and his colleagues from Japan have a collection of paper about Jorgensen number for many groups.
Let me ask a question. So you just talk about the Jorgensen number of a group.
Yes.
It is defined only for those groups that lie inside PSL to C and are discrete.
Discrete and non-elementary.
And non-elementary.
Because Jorgensen inequality is the theory about S condition for discrete non-elementary group.
So there is no way to extend it to arbitrary groups or arbitrary subgroups of PSL to C or subgroups of PSL N, C.
I can make a remark a little bit later when I will talk about elementary groups. for some elementary group, this infinitum equals 0. But for some, it is not equal to 0. I will show you and we will experiment. So, Picard group is extreme group for Jorgensen inequality. It is there exist two generators for which a Jorgensen inequality equals 1. All extreme subgroups of Picard groups are listed, and there exists the following theorem was proved by Ricci and Sata. If we consider some natural number n, then there exists a group with Jorgensen number equals n. And for any real number which greater than 4, there exists a group with Jorgensen number equals n. The first family of groups are some generalization of modular group, and the second family is the family of Schottky groups. Sata is specialized in Schottky groups. They have many papers on this subject. So we considered some classical objects, Jorgensen number, Jorgensen group, and we know that there exists an infinite series of extreme group, and we know that there exist groups with Jorgensen numbers from R, from real Jorgensen number. What about analysis of Jorgensen inequality? Suppose two elements, now they will generate discrete group, not non-elementary but discrete. Question proof as analysis of Jorgensen inequality the following. Do there exist other constraints A and B such that the following Jorgensen type inequality holds? And we know two answers on this question. First was introduced by Gehring-Martin and Tan. Suppose that two elements generate a discrete group, and we have this restriction of the commutator of generators. Then the following inequality holds. We will denote the left part of this inequality by G, Gehring-Martin-Tan. The second answer is the following. Suppose that we have two elements and they generate discrete group. If this restriction holds, then the following inequality holds. In this case, we have constants A equals 2 and B equals 1. In this case, we have constants 1 and 0. We will denote the left part of Tan inequality by TFG. What about
So these numbers A and B depend on the group or depend on F and G?
These numbers, okay, they arise from the following. We consider group generated by two elements.
Right.
This group discrete.
Right.
If it is non-elementary, then Jorgensen equality holds.
Okay.
If this restriction holds on generators and group discrete.
No, the first question, there's this constant A and B, right? So you could take 0 and 0, it's almost
if you take two constants, 0 and 0, you must prove that this inequality, the result of inequality will be necessary to this condition. So we can, these constants not...
They are before group. They are before group. So other than some constant.
So the constants belong to the group, not to the elements.
They before.
The only constants that not these constants A and B don't relate it with elements F and G.
So the,
So universal constant.
So other than this
for every two generated group.
For every
For
two,
every
What's
generated
what's wrong with 0 and 0?
For every discrete two-generated group
It's
with such generator that is
you want to, for any two F and G in the set to C that generate a discrete group,
Yes.
eventually non-elementary,
Yeah.
you also have this inequality.
Okay.
Can
Zero.
you find such
A equals 0, B equals 0.
So it can be Moriah inequality.
Right.
But-
So,
I don't understand. I don't understand the sentence.
Maybe I give some sketch of proof of this theorem. Okay. So if we have discrete group,
Yes.
which is discrete subset of PSL to C,
Okay.
okay, then it is not have
sequence.
sequences tends to identity elements. Okay.
Right.
Okay. If Gehring-Martin and Tan show that if we have groups on two generator and these not both, then we can construct a sequence in this group which tends to 0. That's why group will not be discrete. Contradiction. Okay. And we're interested in extreme cases. We are interested in groups for which in these inequalities are equalities. Here and here. I will say now about it. So let us consider, G means the left part of Gehring-Martin-Tan inequality, and T means the left part of Tan inequality. We will define two numbers, Gehring-Martin-Tan number and Tan number, by analogy with Jorgensen numbers. And we will consider groups for which there exist two. Okay, I think that I must read the definition. So let us consider the group which are to generate and discrete. The following value we will call Gehring-Martin-Tan number, and the following value we will call Tan number. There exists extreme group for which these numbers equals 1, and there exists generating pair on which this equality holds. In what question we interested? So we have some analogs on Jorgensen inequality, on Jorgensen numbers. What about analogs of properties of Jorgensen inequality? And we will consider only a class of elementary subgroups of PSL2C. I recall that the group PSL2C acts on the interior of hyperbolic space and its boundary, and elliptic elements fix the geodesics and in H3. More precisely, elliptic element acts on H3 as a rotation about some geodesic. A parabolic element has unique fixed point on the boundary. In fact, a parabolic element is a rotation around a boundary point. And a loxodronic element has two fixed points on C. In fact, loxodronic element is the translation from one point on boundary to other. Okay. And as I said, elementary group is the group for which there exists a finite orbit in this set. We know classification of all elementary groups. For this classification, we need a definition of limit set of the group. So given a sum of G, denoted by lambda G, the limit set of this group in the boundary. I mean the set of accumulation points of orbits from H3 in C. Accumulation points. And the following proposition takes place. Let G be a discrete elementary group, then limit set of this group contains 1, 0, or 2 points. When this limit set is empty, then G contains only elliptic elements and identity elements. If this set is one-point set, then G contains parabolics and does not contain loxandronic. If lambda equals 2, the number of elements of lambda equals 2, then G contains loxodromic and does not contain parabolics. So let's refer to these groups as elliptic elementary groups, these as parabolic, and these loxodromic groups. Okay, what we have for these groups? Lester Ford, in his monograph The Automorphic Function, described all elementary discrete subgroups with empty limit sets. And he showed that if the two generated discrete elementary subgroup of PSL to C and the limit set of this group is empty, then either G is the diagonal group, or G is a rotation group of regular tetrahedral group, G is octahedron group, or G is a hedron group. So in these three pictures, I write the axis, the type of elements in the last three groups. This is regular tetrahedron, and its symmetries. This is octahedron, and this is icosahedron. Groups of rotation in each case realized as the group of hyperbolic orientation isometers. And we have the following Tan and Gehring-Martin-Tan numbers for these groups. First, 6 lines are Pietro groups, and they are interesting because D4, D5, and DT, where D is prime, is the series of extreme group for Jorgensen, for Gehring-Martin-Tan inequality and Tan inequalities. Moreover, A4, the tetrahedral group, is T extreme for Tan inequality. That's why we have the infinite series of Gehring-Martin-Tan and Tan groups. Another classification theorem is about the case when the limit set of elementary discrete group has one element, and if G is, then G is either parabolic group of rank 2, either infinite diagonal group, or one of Euclidean triangle groups. So triangle groups in this case defined as in Brewer's case, but we consider Euclidean triangles. For first group and we consider the group generated by rotation in vertices of right triangle, and other groups arise by the analogous way. We know all Gehring-Martin-Tan and Tan numbers for these groups, and we see that the only Gehring-Martin-Tan group in this list is one. Exactly group generated by two rotations, rotation on angle pi over rotation by angle pi and pi over 2. Okay, we know all this now. And the last family of discrete elementary group is the family with limit set containing two different points on the extended complex plane. There exist two families. The first is the groups which two generated, such that F is loxodromic and have two fixed points, and G an elliptic element of finite order, and it has the same two fixed points. This group is abelian and isomorphic to the following group. Another family of groups is the following. We have two generators, F loxodromic element, and G is involution, half-turn, or another elliptic element of order 2, which interchange fixed points of F. For this first family, we have only estimates on Gehring-Martin-Tan Gehring-Martin-Tan numbers and Tan numbers. And what we see from these estimates, first of all, this group is extreme because the case where we have n equals 4, this guy is equal to 2, and we have the lower estimate and upper estimate are the same. And what we see from the second to second equality, we see that all groups of this family have they are not extreme for Tan equality because Tan number found below by constant 2. And for the second family, we have this theorem. We know exactly what numbers have this group. So the Gehring-Martin-Tan numbers we have this formula for Gehring-Martin-Tan number and this formula for Tan number. And why these formulas are interesting? Because the corollary from this theorem is theorem 5. Let us consider the real number which greater or equal to 1. Then we can construct infinite family from this family for which Gehring-Tan number equals R. And in this family exists infinite subfamily for which Tan number equals R. Okay. What did I talk? First of all, we consider Jorgensen numbers and Jorgensen equality, and consider some results about such groups. And then we construct analogies for this inequality and for these numbers and groups. Okay, I finished. Thank you very much for your attention.
Questions, please?
So are these numbers are true infimums or they can be realized by a pair of generators?
Oh, all these for elementary groups, all these numbers are realized. I know the pair of generators in terms of matrix for which GMT and T number equals this value.
But for non-elementary it's not the case.
Oh, I don't know because I found this question in other articles and we don't have an example of group for which we know Jorgensen number and which doesn't have a generating pair with this Jorgensen number. All groups that we know for which infimum is there existed power generators for which infimum equals to Gehring-Martin-Tan number from this pair of generators. We don't know example.
Other questions? So, is there any generalization for PSL and C for this inequality?
Jorgensen inequality is closely related with a hyperbolic geometry. That's why there exists generalization of this inequality for hyperbolic spaces, not dimension 3, but 4. Our colleague from India, Krishna Sakhaya, interested in this question, and he constructed an analog of Jorgensen inequality for PSL to H, where H mean quaternions. Okay.
I want to make just one strange remark is that the numbers you have got, like 4 minus sinus square, recall a lot John's indices of subfactors. He also had a discrete series of numbers of type 4 minus cosine square. We had a continuous range of all numbers greater than or equal to 4. So I just wonder if there is any connections whatsoever.
It's observation, yeah?
Yes, it's just an observation. I just observe looking at the numbers.
Thank you.
Just a remark.
There is deep connection maybe.
Maybe, yes, but you know, we don't
So deep.
so deep, yes.
If you have more generators, the
Oh, one of the most incredible corollary of Jorgensen inequality is the following. Any two-generator non-elementary group is discrete if and only if each two-generated subgroup of the group is discrete. That's why we go from a group with n generators to group with 2 generators, and that's why we're interested on the input.
but there are no generalizations of those inequalities for more generators.